Today we're going to look at transformations of the graphs of sine and cosine. Before we do that, I want to make sure that we've got some vocabulary under our belt here. So first, a reminder of the midline. So midline refers to the horizontal axis that runs through the center of the graph, whether it's sine or cosine. Another word that you might see that's the same as midline is, spell that correctly, sinusoidal axis. So sinusoidal, takes me 3 tries here, sinusoidal axis. So sinusoidal axis and midline mean exactly the same thing. It's the horizontal axis right through the middle of a graph. The amplitude, it's not a highlighter, the amplitude is the vertical distance from the midline, so from the center of the graph, to either the maximum or the minimum of the graph, so the highs and the lows. And again, that if we're talking about amplitude as a distance, it's always going to be a positive number. The period is the length of one cycle of a periodic function. And so for our original sine or cosine, our period is 2 pi because that's the length it takes to get around one circle. Frequency is a new term for us here, and it's related to period. Frequency refers to the number of cycles per given interval, which is usually 2 pi or 360 degrees, unless stated otherwise. So if period is the length of a cycle, frequency is the number of cycles in 2 pi or 360 degrees. And so we'll see as we start to change the period, that will change the frequency and vice versa. Then our last term here is a phase shift, and that's just a fancy term for a horizontal or left or right shift of a periodic function. So just like we can shift other function families left or right, we can shift sinusoidal graphs, periodic functions, left and right and up and down as well. And that's a little bit of what we're going to be doing today. So our general form for a sine, and we're really going to do a lot of our work today in terms of sine rather than cosine, just to give us some place to start. But before we do that, I want to explore these a little bit. So there's kind of 4 transformation values that could impact our graph. A sine of b times the quantity x minus c plus d. So let's take a look at each of those here. So I've got a graph of sine. It starts at 0, 0. It has an amplitude of 1 and a midline of 0. So let's take a look at that a value. If I change that a value and make it bigger, the graph stretches. So the amplitude, that vertical distance between the midline and either the maximum or the minimum, gets larger. And so we can, it goes off the screen, but we can make that amplitude larger. Now, if we were to have a negative amplitude, like a -1, you see it's a reflection over the x-axis. So instead of going from 0, 0 up to pi over 2, 1, it goes down. And so it just kind of reverses it. We would still call it an amplitude of 1 or 2, whatever that is. We would just think about it as a reflection. But in general, the a value changes the height or the stretch, the amplitude of your sinusoidal function. Set that back to 1. I'm going to actually go a little bit out of order. I'm going to look at the d value. So that's it's got a little bit cut off here, but it should be plus d at the end. So let's see what happens when we change the value of d. If we make d bigger, the graph shifts upward without changing any other aspect of its shape. If we make d smaller, the graph shifts downward. So d changes the value of the midline. If d is a vertical shift up or down, c is a horizontal shift. So c gets a little bit tricky. Our horizontal shift gets a little bit tricky here because since this is a periodic function, depending on how far I shift, it can be hard to tell, right, whether I'm shifting, just a little bit or more than 2 pi. So we'll talk about some ways to figure out a C value or work with a C value in practice, but I just wanted you to see that it shifts left and right. And then finally, this B value. Notice it's being multiplied in the expression times the quantity x minus C. It's inside the sine function, which is different than where the amplitude is. If I make B bigger, so let's see if I make it 2, look at what happens. Our graph is more squished together, kind of from side to side. And if we look even closer and kind of trace along here, we actually have 2 cycles of the sine fitting between 0 and 2 pi. When B was 1, we had 1 full cycle. When B is 2, we have 2 full cycles. If we make B even larger, like 3, we can trace this and see that there's 1, 2, 3 full cycles within 2 pi. So B changes the frequency of the graph, and therefore it also changes the period, and we will look at how we could compare those. But for now, I'm going to change that back to 1. And I just want to show you really quickly that all of these transformations have the same impact as cosine. So here I have cosine, and then cosine B times x minus C plus D. So we can see that as we change, the midline, it still moves up or down. Our horizontal or phase shift. So all of those transformations, whether it's sine or cosine, still apply. But like I said, today we're going to focus more on sine. So let's go back and add to our notes here. So this A value will affect the amplitude, right? And if we want to add to that, that's kind of a like a vertical stretch or shrink, depending on if we make A bigger or smaller. Our D value will affect the midline or the position of the midline, so it will shift the graph up or down. The value of C, represents that phase shift, and so again, that's either left or right. And then B represents the frequency of the graph, how many cycles occur within 2 pi. So we're going to do 2 kinds of examples here. We're going to do examples graphing from an equation, and then we're going to write equations from a graph. So we're keeping all of this in mind, and I think I'm just going to highlight this so that it stands out as we need to refer back to it. So let's start by making a reference graph of sine for ourselves. So sine starts at 0, 0, and then at pi over 2, 1, and then it goes back down to 0 at pi, goes to -1 when x or theta is 3 pi halves, and then goes back up to 2 pi. And then in negative theta direction, right, it's kind of exactly reversed. And so we get this periodic smooth curve. Try to make it look as nice as possible. There we go. Okay, so we've got our original sine of theta. So let's graph 2 sine theta minus 1. So we've got 2 transformations that occur here. This minus 1 will shift the midline down 1 unit, and then this 2 will make the amplitude 2, right? So it'll stretch it a little more than our original sine. So my midline, I'm shifting down to -1. For myself, I like that visual so I can see where exactly my maximums and my minimums will be. Everything else will be more or less the same here. It's just kind of how tall those peaks are. So if I think about the starting point 0, 0 has been shifted down just to 0, -1, I can plot that point. But then if I know that on my parent graph it will kind of go up to its maximum of 1, here, since my amplitude is 2, instead of going up to a maximum that has an amplitude of 1, it'll go up to a maximum that has an amplitude of 2. So in this case, it'll be at the point I halves 1. It goes back to the midline, right, at pi. So this, our transformed graph should go back to the midline at pi as well. It drops below the midline at 3 pi halves, and in this case, below our midline will be at 3 pi halves -3, which got cut off the graph there, unfortunately, and then back to the midline at 2 pi. So I think it helps to have the midline kind of sketched there so that we can at least understand the direction of the path that our graph is traveling, and then we can fill in details like the amplitude from there. And then again, go back in reverse, make sure we're hitting the midline at those specific intervals. You might see on some resources that those points where it goes through the midline are called points of inflection because it's switching from, a concave up to a concave down kind of shape there. But we have a graph that has a midline at -1 and it has an amplitude of 2, right? That vertical distance from midline to either the maximum or minimum is 2. Our third example is really the same as our second example, right? It has that amplitude of 2. It has a vertical shift or midline at -1. And what we have going on in here is a phase shift, a horizontal shift. So thinking about that horizontal shift and what we know about earlier transformations, what direction is this going to shift our graph? It's going to shift our graph to the right pi halves units. So this time, instead of our graph starting at 0, -1, like in our last graph, we're going to start at, oops, and I do want to put the midline in there, sorry. We're going to start at pi halves -1. So we're recreating the graph that we made just before, except for we're shifting all of those kind of key points to the right pi halves units. So it's not just that, and I say starting point with air quotes around it, but it's every other point on there that's also being shifted to the right pi halves units. And then we can go in reverse again. Oops, come on. So we get a slightly different kind of perspective of this picture. But the long story short is that we've got all the same as our second graph. It's just that we scooted everything over to the right pi halves units. Now, our fourth and final example again includes everything prior to it, but we also have now a new frequency. So if we were to think about our last graph and maybe trace that frequency there, I'm going to use yellow to trace the frequency. If we think about the time it takes to travel one cycle, that is still a period of 2 pi, right? It's just been shifted a little bit. If it's easier, we could think about, well, from 0 to 2 pi, it's still really one full cycle because it's going from minimum up to maximum and back down to minimum, and it would repeat that over and over again. So for our fourth graph here, we're going to have a frequency of 2. which means that in that same period of 2 pi, or within that same interval, I should say, since period does have a specific definition, we're going to have 2 cycles in the interval of 2 pi. So there's a couple of different ways you can think about this. And again, it really depends on your reference here. If you prefer to reference the midline or you prefer to reference the minimums, you might have to find something that works best for you. I'm actually going to reference the minimums and kind of use this idea from 0 to 2 pi. Now I know that I'm just going to have 2 cycles within that, which means that from 0 to pi, it's going to have to go back down to its minimum in the middle of that, rather than at the end of 2 pi. So let's see if I can get this on the first jot. So 0, -3, and then instead of having that, it's going to hit the midline at pi halves, it's going to hit the midline at pi fourths and go up to the maximum at pi halves. Basically, the distance between all of these reference points has been cut in half in order to squeeze a second cycle in there. So it might help to just kind of see the rest of this here. But now, in that same interval of 2 pi, I have 2 full cycles of this graph. So this certainly takes a little bit of practice, and again, a little bit of, I would say, self-discovery, like what reference points are going to work best for you. Because the reference points that work best for you may not be the same reference points that work best for me or work best for your friend. So don't take that personally, and don't feel like you have to do it any particular way, as long as we're understanding kind of what's, the big picture of what's happening here. When we increase the frequency, when we say, oh, instead of 1 cycle, we're going to have 2 cycles, that means that cycle has to be squished in there by a factor of 2. So this takes a little bit of practice, a little bit of practice. Whatever you need is what you need, and that's okay. So there will be some practice questions for you to do your best with. Let's switch gears here just a little bit and actually write some equations based on the transformations that we see. And notice the instructions here that we're going to write in terms of sine. Since sine and cosine, you've seen, are really related graphically, we could technically write all of these in terms of cosine as well. But just for consistency's sake, I would like to use sine just like we did up above. So that would be a sine of b times the quantity x minus c plus d. So let's take a look at what we've got going on here in example 1. I like to start with the midline because it gives me a really good reference for everything else. So my midline appears to be at y equals 0. So there's been no vertical shift at all. So I don't have to worry about that. That amplitude has been changed just a little bit. Our amplitude now from the maximum or the minimum to that midline is 3, right? It's a distance of 3 units. Okay, so I know that my A value is 3. Maybe I should also indicate that here I know that my D value is 0. Now it goes through the point 0, 0, which is a kind of, again, that start rate in air quotes there. So I'm going to say that there are no phase shifts here. It has not been shifted left or right. And then I just want to kind of see how many cycles or what the frequency of this graph is. So from 0 to 2 pi, there is only 1 cycle. It's very little, but that is 2 pi there. So there is only 1 cycle. So there's been no phase shift, and our b value, our frequency, is 1. So our graph here, our equation of our graph, is simply going to be 3 sine theta or 3 sine x, depending on what variable you're feeling most comfortable using. Either one's going to be fine here. We don't have to put that the b value is 1, right, because a ninja 1 doesn't change the value. So let's take a look at example 2. Again, our midline is at 0, so there's been no vertical shift. This time, our amplitude is 1, so there's also been no change there, right? So our a value is 1. Now, from 0 to 2 pi, now I'm noticing it is kind of starting in a different position. I'm going from maximum to maximum in that interval, but that's okay. That again tells me that my frequency is 1. But what has changed is that instead of my graph starting at 0, 0, it seems to be starting at the point 0, negative pi halves. Now, if we think about what we know about horizontal transformations in the past, we're going to put this in our formula here as x plus pi halves. So our equation for our graph here, y is equal to sine. Again, if we have an amplitude of 1, we don't actually need to write that in. If you'd like to write that in, fine, cool, of theta plus pi over 2. And again, when we think about our horizontal transformations, there is a minus sign built in, so that's why we're using the opposite there, or kind of in our mind, it's the opposite of what we want it to be. It is, in fact, left pi halves units, even though it says plus 2 pi. All right, just a couple more examples to get us all used to the idea. So example 3 it looks like maybe there's been a change in frequency. So maybe we'll start there. If I start at 0, 0, and I'm looking, where is 2 pi? 2 pi is right over here. I'm going to have 1, 2, 3, 4 cycles. Remember, it's a complete cycle, so not how many maximums or minimums, even though they definitely coincide. We should be thinking about this always in terms of cycle. So we have a frequency of 4, which means our b value is 4. It does appear to start at 0, 0, so our c value is 0. There's been no horizontal shift. Our midline also, incidentally, is at y equals 0. So no midline shift there, no vertical or horizontal shift. And then last but not least, forgetting about our amplitude, our maximum is at 2, our minimum is at negative 2, which means that we have an amplitude of 2. So our equation here is going to look like we really have to just incorporate that amplitude and that frequency. It's going to be 2 sine of 4 theta, or 4x. Again, I'm not too worried about the variable you use there, but our 4 is in reference to our frequency, 4 cycles per 2 pi unit, or per 2 pi intervals, and an amplitude of 2. All right, one more example here. We're doing a great job. Well, what's the first thing that I observe here? Any guesses? I've noticed that my midline is no longer at 0. It's at 2. It's at the line y equals 2. So I am going to have a vertical shift there, shifting my whole graph up 2 units. My amplitude, though, if I think about, oh, what's the distance from 2 to 3, or 2 to negative 1, that's going to be an amplitude of 1. It looks like there has been a phase shift here, right? The center or kind of start of our graph. It would be, if this was unshifted or not shifted in the horizontal direction, it would be at 0, 2, right? Because that would be just shifting it upwards from 0, 0. But this looks like it's been shifted halfway between pi halves and 0. So halfway between pi halves and 0 is pi fourths. So our C value is pi fourths. And then if I want to think about how many cycles there are per 2 pi intervals, well, there's again kind of a couple different ways I can think about this. I can go and notice that if I trace this for one whole cycle, so back to midline, it seems to do that on the other side of 2 pi or 5 pi. Oh, is that 5 pi fourths? That would be 9 pi fourths, which is a total distance of 2 pi. That would be a frequency of 1. Or I could think about it, oh, how many cycles from the y-axis to 2 pi, and I would just have to notice that it's not on a maximum, minimum, or midline. It's on a different point. So whatever our perspective is here, again, you're going to have to find what works best for you. But either way, I do have a frequency of 1. There's only one cycle in any 2 pi length interval. So our formula here is going to look like y equals, now I'm going to write out every piece here. We have an amplitude of 1, right? We have a frequency of 1. We have a shift of pi fourths to the right pi fourths. This will be theta minus pi fourths. And then we have a vertical shift up 2. So if I'm going to simplify that, I'm going to simplify that as simply sine theta minus pi fourths plus 2. So there's a lot that I've thrown at you here. However, it's kind of, the first piece is, what are those kind of landmarks for us, right? Our amplitude, our frequency, our midline, and then shifting left or right with our phase shift. Those are the 4 things that we're going to kind of have to run through and piece together with each of these. So it's a little bit of a logic puzzle, making sure that we cover all of our pieces, but you've done really well with transformations in the past, and I know you're going to continue to do well and do the best of your abilities today.